Search. So what we're interested in today and for the next 5 lectures is to come up with a formalism to allow agents to plan ahead. We'll formalize the problems we try to solve as search problems, and this will be an abstraction, a mathematical abstraction of a general class of problems. And once we've abstracted a problem as a search problem, then any of the algorithms we'll look at will be able to solve that problem in that abstraction. And we'll look at various different algorithms. Today we'll look at the first 3 algorithms, depth first, breadth first, and uniform cost search. And we'll see more algorithms to solve those problems in future lectures. Okay, agents that plan. What do I mean with that? The idea here is that an agent is supposed to achieve a goal. Could be maybe reaching an apple. But there might be different ways to try to achieve that goal. There might be different ways of acting that don't even achieve the goal. And a planning agent will think about different ways that their actions could play out ahead of time in their head or inside a computer, and then pick a plan that in the computer was simulated to have a high chance of success. Let's first contrast these planning agents with something that's maybe a little easier to program, reflex agents, but not necessarily as powerful. Reflex agents are agents that choose their actions just based on the current state of the world. So it's an example of a reflex agent. Let's say you have a bug that's about to fly into your eye. Most likely you'll wink to keep the bug out of your eye. That's a reflex agent policy. Why? You just react to the bug coming to your eye by closing it such that it doesn't get into your eye. What would planning be in this case? A planning agent would say, oh, let me think about this. If I keep my eyes open, then the bug will hit my eye, and this might cause some annoyance. If I close my eye, then it'll work better. And after having thought through the 2 different scenarios, it'll decide, okay, the right thing to do is to close my eye. That's a planning agent, simulating what would happen and then based on that making a decision, whereas a reflex agent just says, okay, this is the situation, a bug is coming at me, I'm closing my eye without thinking of the consequences. Fundamentally, that's the difference. A reflex agent doesn't think about the consequences of its actions. It might still take good actions, but it doesn't think about the consequences when deciding what action to take. Reflex agents, can they still be optimal? Can it be rational? Can it maximize expected utility? Right? Last time we said what we want to do here is maximize expected utility. That's what we're trying to do. Well, let's look at an example. Here's an example. Pac-Man is programmed to be a reflex agent here. Pac-Man is programmed to just look around itself, find where the closest dot is, and choose the direction to move in that brings Pac-Man closer to the closest dot. Let's see what happens when we play this out. This is a pure reflex agent. And this was actually optimal. This was the optimal way to clear this board if the goal was to eat all the food pellets. So this is an example of a reflex agent that in this situation does the right thing. Do they always succeed? Here, the same piece of code, but a different world that the agent has to act in. Again, moving to the closest dot, or in the direction of the closest dot. So it's going west here. Here's going east, 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 and keeps trying east because the closest dot is towards the east, and nothing happens. You even see the score go down. In the Pac-Man problems we'll look at in this course, every time step that goes by, you actually lose a point to encourage you to get to things sooner rather than later. Question?
The Pac-Man agent there, when it had multiple dots were all equally close, was there something random choice between them, or did they preset certain directions?
It was just breaking ties in some way. In this case, it broke ties where west was favored over other directions. In almost everything we do, in principle, tie-breaking shouldn't play a role. You should have algorithms where the tie-breaking is not the most important thing to get good performance. But often we do have to tie-break, and we'll have some pretty arbitrary scheme. To make it consistent, often we'll say something like, do alphabetical tie-breaking. If you have labeled actions, pick the one that's alphabetically first if you need to break ties. All right, so in contrast, planning agents, think about what would happen. They ask the question, what if I were to take this action, and then followed by that other action, followed by yet another action? What would the world be like after that sequence of actions? Of course, there's many sequences of actions to consider, and the whole game here of what we'll be studying is how to efficiently consider the most relevant sequence of actions such that we can find a good sequence of actions that we can then act upon. One notion we want to think about when we think about planning algorithms is whether they're optimal or complete. Optimal means if they return a solution, that solution is the least cost solution. So we might want to have an algorithm that does that for us, rather than just an arbitrary solution. Complete means if there exists a solution, there is a path that gets you to the goal, it will actually find a solution. Another notion that will be important is planning versus replanning. So as you make your plan, you generate your sequence of actions. You could say, well, I'm just going to execute on that sequence of actions. That might be fine. If your world is deterministic, you have a perfect model of the world, then you can plan a sequence of actions, act on that, and things will go as planned. In future lectures, we'll see that not always you can predict what the consequences of your actions are, and then you might want to replan. You might come up with a sequence of actions, start executing, then you see what the world actually became like, and plan again. And so you will continuously be changing your plan as you execute. Another reason to replan could be to make shorter plans. So rather than plan all the way till the end of the time that you get to act, you might only plan, let's say, 10 seconds ahead. Execute that plan, and then after you've executed the plan for a while, you again plan only looking 10 seconds ahead. The reason to do that is because the further you look ahead, the more expensive it can become to plan. So let's look at an example here. The first one we'll look at is what we call mastermind Pac-Man. The algorithm underneath is something that we will understand at the end of next lecture. But for now, let's just take a look at how mastermind Pac-Man cleans up this board. So it starts computing, so it's planning. You see the prompts up there saying it's done with pre-calculations. It's still computing other things. It's testing out different sequences of actions, see what the consequences would be. It's tried 1,000 nodes so far, 2,000. Still thinking. Now I found a plan that it knows is the optimal way to clear the board, that is clearing with the minimal number of steps. Here it is with a score of 914. Question?
So you said that you lose a point per time interval passes, but what if you had no points already? So what if you're inaccuracy was just waiting for a long time pre-planning? If that time wasn't actually considered in terms of the job.
So the way we set it up is that we tend to give you a preset time to think. So you might get, let's say, 10 seconds to think before you start acting. Then the game starts, and once the game starts, every time step in the game will cost you a point. Every time you hit a food pellet, you'll actually earn 10 points. So that was Mastermind Pac-Man. Really high score. But it took a lot of computation to start out with. Now let's look what happens if we do something a little more naive, a replanning. So what's implemented underneath here is not trying to find a plan that clears the entire board, which is a very long horizon plan. They'll just try to plan to go to the nearest food pellet. It's not the same as the reflex agent. The reflex agent looked in which direction is the nearest food pellet and move in that direction. This one actually checks on the board where is the nearest food pellet, then finds a path towards that nearest food pellet, executes that path. Once it reaches that nearest food pellet, it plans again. So this one essentially takes no time to think and can think as fast as it's executing as it goes along. Clears the board pretty well, 907, a lower score than Mastermind Pac-Man, who got 914. But still a pretty good score, and sometimes that's what you might want to do. Maybe the trade-off is that you don't want to sit there thinking for too long. You don't have the time to think for that long. You want to just execute, and then replanning might be the way to go. You'll see both versions in your project one. Okay, so what is it that we're trying to solve? Search problems. What does a search problem consist of? It consists of a state space. The state space is your abstraction of the world. You take that part of the world that you think matters and that you're going to be thinking about in your simulation of how things could play out. In the case of Pac-Man, let's say Pac-Man is in a board of 3 by 3. These are various states in the state space, but there are more states in the state space than the ones shown. So there are more states here. Typically, there can be a very large number of states in your state space, and we will not enumerate them ahead of time. This is just for illustration purposes. These are example states in the state space. A successor function. A successor function is something that prescribes to you, if you are in a particular state, and you were to take a particular action, what is the next state going to be? It'll also tell you if with that action, if there's any cost associated with it, how much that cost is. So a way to visualize as follows. If we were in this particular state over here, we have 2 actions available to ourselves, going north or going east. The successor function encodes that these are the 2 available actions. It encodes the cost for each of these actions. Taking an action makes 1 time step pass, so it's a cost of 1. And then it also encodes the respective next states that you would land in after taking that action. In addition, we need a start state. That's where the agent is going to start. And we need a goal test. What I mean with goal test? Typically in search problems, there might be more than one way of achieving our goals. Let's say the task is to clear the board from all food pellets. It might not matter where Pac-Man ends up, as long as all food pellets have been cleared. In that case, in this particular scenario here, there would be 9 goal states, 9 ending locations for Pac-Man where all the food pellets have been cleared. And so we say there is a goal test. The goal test is a piece of code that checks, in this case, whether all food pellets have been cleared. All right. A solution to a search problem is the sequence of actions, which we call a plan, that transform the start state into the goal state, or one of the goal states. In practice, if you're working on real-world AI problems, usually you'll spend the majority of your time on this part here. You'll look at a real problem, you'll try to abstract it away, because the real world is very complex. You'll abstract it away into something simpler that you think has a reasonable simplification of the real world for what you're trying to do. Set up a state space, successor function start, and goal test. And then you'll just call some piece of code that generates the solution. And that's kind of key here, that once we formalize something into a search problem, at that point, it's an abstraction, and our search algorithms will be able to solve any real-world problem that we abstracted into a search problem. So we go from real-world problem to search problem, and then the search algorithms will be able to solve it. They'll just access abstractions such as calling for the start state, calling a goal test, calling the successor function, and that's all the search algorithms will have to do. Okay, so search problems tend to be just models, that is approximations of the real world. So let's look at some examples. Here's a pathing problem that you might encounter in the real world. Let's say you are in Romania, and you are in the city of Arad, and you need to get to the airport, which happens to be in Bucharest, over here. And you now want to find, let's say, a path that gets you from Arad to Bucharest. How do we formalize this into a search problem? Well, first thing we need is a state space. What could the state space be? In this case, maybe the state space could be which city you are currently in. Okay? That's a reasonable state space, but it's not the only one. If you were to work at a different level of abstraction, maybe the state space would be the GPS coordinates of your car or something, if you want to make a much more detailed plan. But in this particular case, we're trying to make a plan for routing along this roadmap, how to go from our start state to our goal state. All right, successor function. In this case, we could say, well, from any given city, we can look on the road network what the neighboring cities are, and then successor function would have the roads going to adjacent cities with a cost associated with it, which corresponds to the distance. Again, distance here, that's a choice. You might choose something else. Maybe you choose the time it will take to traverse that particular road link. Or you might choose the amount of gas that you expect to have to use to traverse that particular road link, and so forth. So again, these are choices you make, a way to abstract your real problem into a search problem. Start state, well, we're starting in Arad, so that's going to be the start state. Goal test, in this case, there's only one way to achieve the goal. It's whether you achieve the goal if you're in the city of Bucharest. So, is the state equal to Bucharest is our goal test. Solution? Well, the solutions will be, in this case, the cheapest path from Arad to Bucharest, and we'll later look at how we algorithmically confine that solution. Okay, let's look at a couple more examples. Here, we have a Pac-Man world. What we show at the top here is what we call the world state. The world state consists of everything that we can think of that relates to this problem. And then, when we want to solve a particular problem, we come up with a search problem abstraction. And let's say the problem is pathing. Meaning, Pac-Man starts in a particular location, needs to get to a particular other location. And what would be our search problem formalization? Well, let's think about this. So, how about states? X, Y coordinates for the location. We need that to properly be able to think about pathing, right? What do we need for actions? There's 4 actions available, so that's just the action space, north, south, east, west. Successor function will tell us how to update the location. So if we move, let's say, north from a particular location, if there's no wall, then indeed we move one spot up. The goal test will be whether the x, y coordinates are equal to the end state. One thing to keep in mind when you design your state space, which is usually the first thing you do, is keep in mind whether you can actually define all the others just based on your state space. So you need to make sure that your goal test only accesses the state, no information outside of the state, because otherwise you can't really, you don't have a sufficient state space. You can't check whether your state is achieving the goal. Same for the successor function. You need to make sure that your state space contains enough information that you can define your successor function. Okay, let's do another one, and let's do this one together. Now the problem is to eat all the dots in this board. What's a possible state space? So I hear location. I hear food location. I hear ghost location. Say that again? The power pellets. Those are the big ones. Wall location. Okay. Let's say wall here. Or walls, plural. Ghost location is here. Oh, ghost, scared or not. What was that about ghost? Oh, where the ghost might respawn point. Okay. All right. So let's take a look at what we have here. What we have here is what I would call all the information we need to simulate this game. Let's call this game the real world for our purposes here. So the actual game is the real world. So what we have here is the real world state. Everything we need to play the game. The question, however, is, do we need everything in the state of our search problem that we have listed here, or can we get away with less? Okay? So let's look at one thing here, for example. Walls. The walls are something that doesn't change throughout the execution of the game. They stay put. Things that don't change throughout the execution are not things we put in the state space. Think of the state space as the variables that vary as time goes by. So walls are not needed there. They can be somewhere sitting separately, but don't get updated by the successor function, don't play a role in the goal test, and so we don't need them. Then let's take a look here at a couple of other things. Respawn point. Assuming that's a fixed thing where they respawn, that's similar to the walls. It's something that doesn't change as the game evolves. It's always the same thing. You can always go look that up. It's not part of the state. It's not part of the variables that vary as the game is being played. Okay, then here we have power pellets, ghost location, and ghost scared. So those all relate to the ghosts. The way we phrase the problem here, and there's a little bit of fine print here that I'll clarify, is eat all the dots. And let's, for now, assume that the ghosts just don't eat you. Right? The problem is just to eat all the dots, ignoring presence of ghosts. In that case, we can make a further simplification, and we can get rid of whether the ghost is scared or not, what the ghost locations are, and where the power pellets are. I'm not crossing those out. The reason I'm not crossing those out the same way, they're in somewhat of a different category. We made a specific assumption here that we don't have to worry about the ghost. That's why we can not have those in the state space. Even while they're not in the state space, they will still be in the world state. The world state will have them. It's something that varies in the world, just not for the purposes of the problem we're trying to solve. It's not relevant. What are we left with? XY location and food location. Well, give me some time to go through this, and I'll take the questions at the end of going through the search formulation. So, XY location we need. Otherwise, we cannot define our successor function. We cannot define how Pac-Man moves. Food locations we need because otherwise we don't know where the food is that we still need to eat. You might encode this in different ways. The most effective way to encode this could be as dot booleans. Because at the start of the game, it's fixed where the food is, and then all we need to store is whether the food is still there or not. A 0, 1 for each location where a food pellet was at the beginning of the game, whether the food is still there or not. Okay, so for this problem we end up with x, y, and the dot booleans. Actions, still north, south, east, west. Successor function updates the location of Pac-Man and updates that boolean, whether food has been eaten or not, if you move into a food location. And then the goal test is whether all booleans have become false for all these food dots. Was still a question there?
Yeah. You mentioned that the walls were not part of the state, outside these states. However, what if you don't know the wall location? If your program is given the wall location when it starts the game, is that not in a state because you can't hardcode it? Then some intended wall.
Okay, so the question is really getting to the subtleties of why would we put walls, when would we put walls in the state and when would we not, right? And does it depend on when you find out that information? And the answer is, it does matter when you find out that information. Let's say your Pac-Man is going around and doesn't have a map of the environment. No map is available. It might have to build a map of the maze as it's moving along. And then you would have to encode that in your search problem, because it's something that's going to vary. In your search problem, you'll see that as you go along, your knowledge of the map of the environment is evolving over time. And so you want that in your search problem as a state variable, how the map changes. If it's something, however, that's fixed, then we wouldn't put it in this state space, because it's not something that we need to vary as we go along. So if you look at the successor function, if the map is fixed, the successor function will access that map to compute its updates to say, well, it's possible to move north or it's not possible to move north. But it will not have to encode it in the state itself because it's a fixed thing it can always refer to. Okay, the reason we try to keep the state space small is because very quickly it can become very large and unwieldy to work with. So let's do a little bit of arithmetic here. Let's first look at this problem here. What's the world state? That's kind of everything that's going on in this scenario. We have agent positions. Our Pac-Man has 120 possible positions here, a 10 by 12 grid. The food count initially is 30, so we have 30 booleans to encode about whether that food is there or not. In the world state, there are ghost positions. They have 12 possible locations. And then there are agents. The agent could be facing north, south, east, or west. All right. How many world states do we have? Well, we have 120 positions for Pac-Man times, and this times is important, it's not plus, number of possible worlds, you multiply everything together here, 120 possible locations for Pac-Man times all possible food configurations, which is 2 to the 30, which is a large number, and this is just for 30 food pellets, times each of the ghosts has 12 possible locations, so 12 to the 2, and then times 4 for the 4 directions Pac-Man could be facing. So this is a very large world state space size. Okay. How about the search problem? Let's say our goal is to do pathing here, to go from a start state to a goal state. Well, we looked at what you need for that. All you need is location. So all of a sudden we end up with a state space of only size 120. A lot smaller than the world state space. How about states for eating all the dots? 120 times 2 to the 30. Still large, but significantly smaller than the original world state space. And this will help us when we are running our algorithms if we have smaller state spaces in our search problem. Okay, let's do a little quiz here. So what's the problem set up here? The problem is to eat all the dots while keeping the ghosts perma-scared. What I mean with that is, after you eat one of those big dots, the power pellets, ghosts get scared for a certain amount of time. Let's say 10 steps. During that time, they're scared. And so the problem we want to solve here is one where, and let's assume the first move, let's say, moves you onto this pallet here. So all ghosts are scared in the beginning. And then from then onwards, your task is to keep them scared at all times and eat all the dots. What is the search problem formulation that we can use here? And again, we want to have a minimal search problem formulation because that will help us later in terms of running time. So think about what states, what's your state space, what's your action space, what does your successor function look like, and what does your goal test look like. Let's take a minute or two to think about it, chat with your neighbors, and see what you come up with. Thanks, Alvin. Say it again?
Is the size 120 also?
You can write it as, you can say locations, yeah. All right, what did we come up with for state space? Any suggestions? So I'm hearing position of Pac-Man, I'll assume. So position Pac-Man. Anything else? Scared timer. Anything else? Say it again. Something. Never mind. Okay. So the dot booleans and power booleans. Over there. number of steps to the nearest power pellet. Anything else?
Gosh, I had a question about that one. Would that be built into the successor function? Or is that
Okay, so a question about this one here. Number of steps to the nearest power pellet. Do we need this or do we not need this? A lot of no's. Why don't we need it? The reason is because we can build this into our search algorithm in some sense. We don't need to encode in the state space ideas we have about what might matter to solving the problem. All we need to encode is something that allows us to have a successor function and a goal test. As long as those can go in there based on the state space we define, then it's all good. And the state space should only contain the things that vary among those. So in this case, we don't need the distance to the nearest power pellet, even though often when you code up your search algorithm, this might be something you end up using. It's just not part of a search problem formulation. So these are actually sufficient, right? This is enough to solve this search problem as our state space. So let's clear off the slide, show a typeset. So agent position, dot booleans, power pellet booleans, and the remaining scare time. All right. So what we've looked at so far is looked at real or somewhat real problems for Pac-Man, I guess, and formulated them as a search problem. And as we start moving to algorithms, there's going to be a very important distinction between what is the state space graph and the search tree. So let's take a look at that. So a state space graph is a mathematical representation of the search problem. So let's say this were our start state. The state space graph, which continues up here, by the way, encodes the connectivity between the states. Every state in our search problem will appear only once in the state space graph. So each node here is an abstracted world configuration, and the arcs represent our successor function and might have cost associated with them. The goal test is essentially a test whether you are in a certain subset of these state space nodes. In a state space graph, each state occurs just once. This will be different from search trees. Rarely can you build a state space graph. So think of this as a mathematical abstraction. Once you specify a search problem, you know this graph exists, but you're not going to try to build it. We'll use the abstraction in our algorithms, but essentially what we'll do in our algorithms is find a way to build this part of the state space graph on the fly, building that part of the state space graph that we need to solve the problem. But hopefully never constructing the entire state space graph, because typically that will be completely intractable. Okay, so the toy problem we'll be working with for much of this lecture to illustrate the concept is this very, very tiny search states. So I should relabel this. This is our old terminology. So state space graph. Search graph is just too similar a word to search tree. So let's call it state space graph. So we have a tiny state space graph. In reality, you're not going to care about those problems. If your problem is this small, solve it by hand. You don't need to write a computer program to solve this kind of problem. But for illustration purposes, it's nice to have a state space graph that actually does fit on the slide so we can illustrate what's going on as we execute these algorithms. Okay, what's a search tree? This is something different. A search tree is something we will use in our algorithms. So it's not part of the problem specification. It's something that our algorithms build up as they are running. Our algorithms will always start with the start state. That's the root of the search tree. And then the search tree grows from there. So in this case, there are two available actions, north and east. Those are the two possible futures with one step look ahead. And they're shown here in the second layer of this search tree. And this keeps going. Every one of these states here, this one and this one. From here, there are three possible actions. You'll have successors over here, same here, three successors, and then it keeps going. So a search tree encodes the possible futures you might encounter starting from the start state, following a particular sequence of actions corresponding to each one of the paths in the search tree. The start state is always the root node. So start state is the root node. Children correspond to successors. And nodes show states. If you look at this looks like a state, but it's really important to keep in mind that it's not just a state. This node in the search tree encodes an entire path. So from start state, taking the action north, getting here, that's what's encoded by that particular node in the search tree. And you might have certain states appear multiple times in the search tree, where you might reach those states, that particular state, according to following different sequences of actions. So you might have one sequence of actions that maybe goes this way, reach a certain state, let's call it S, and maybe a different sequence of actions somewhere here also reaches state S. That's okay. A search tree can have that state multiple times, but the plan here is a different plan from the plan over here. Just like the state space graph, you never want to build this entire search tree. In fact, the search tree tends to be even larger than the state space graph, so you really want to avoid building this entire thing. You want to build that part of it that matters to find a solution to your problem. Okay, so here's the tiny, tiny state space graph that we're working with, and here is the corresponding search tree. How do you build that search tree? You start at the start state, look at its successors, in this case, D, E, and P are its successors, so they pop up over here, and you repeat that process from those successors. Okay. Now consider this four-state graph. What does the search tree look like for this state space graph? Think about this for a couple of seconds in your head. Okay? So how do you build a search tree? You start with the start state S. You look at the successor function. You can go to A and to B. From A, you can go to B and to G. From B, you can go to A and to G. Then here, B, you can go to A and to G. Over here, A, you can go to B to G. And this just keeps going and going. The size of the search tree here is actually infinite. This goes infinitely deep. We have an infinite size for our search tree. Definitely, this is a relatively straightforward problem. We would expect our algorithms can solve these kind of problems. So this is another example where you can clearly see our algorithms really need to avoid building the entire search tree to find a solution, or will never be done if the first thing we do is build a search tree. Okay. Of course, there's a lot of repeated structure, and we'll see that in some sense that is what will get exploited. The algorithms will understand that it's essentially seeing repeats of what it's seen before and then avoid repeating that over and over. Okay, let's take a 2-minute break here, and then let's look at our first algorithm for solving these problems. So, tree search. Let's look at a tree search for our pathing problem. We started in Arad, wanted to end up in Bucharest. Let's see what the search tree looks like for this problem. Okay, start in Arad, that's our start state, that's the root of our search tree. If we call our successor function, that would be a piece of code that tells us here are the 3 cities you can reach, the 3 successor states you can reach from Arad, and we'll be able to grow our search tree. Then again, we could call our successor function maybe for CBU, and we'd find that there are 4 successor states for CBU. Note that Arad shows up here. Arad was already here. It's again here. That's okay. The search tree doesn't exclude duplicate states. Here, you were in Arad doing nothing. This node here is being in Arad after having traveled to CBU and then back to Arad. So they're fundamentally different plans. The empty plan versus the plan where you go somewhere and come back. The main thing that happens in tree search is that we build up this tree through calls to our successor function, and we keep track of what is called a fringe. In this case, this is right now our fringe. It's the leaf nodes of the tree we have, the part of the tree we have constructed so far. That's our fringe. Those are the partial plans under consideration. we'll pick one of those nodes in our fringe, call the successor function, and grow our tree. That's tree search. Let's make this a little more formal. So we have a function called tree search. We pass in two things, a search problem and a strategy. More about strategy later. Search problem, we already know what that is. It's something that allows us to call successor functions and do goal tests. All right, so we pass in our search problem. First thing we do is we get the initial state from the search problem object and initialize our search tree with just, or our fringe, we initialize our fringe with just the initial state. Then we have a loop here. If there are no candidates for expansion, what does that mean? We check our fringe. If our fringe is empty, then we return failure, because that means we've been growing this search tree and we have nothing left from where we can grow. Everything in our search tree is a dead end, and we need to return failure. If we're luckier and the fringe is not empty, we choose a leaf node, a node in the fringe, and then the way we choose this is going to be according to some strategy which we'll get to later, but we'll pick some node from our fringe for now. If this node contains a goal state, again, our problem that we passed in has this check built in. We can check if a state is a goal state. If it is, then we return that node which encodes a path from the root to that goal state, and that's a solution. If the node we pick doesn't contain the goal state at the very end, then we expand the node. Expanding means we call the successor function, look at all the successor states that we get back from that, add them to our fringe. The main question here is which fringe nodes to explore. And so the difference in what we're going to do going forward between the different algorithms from now till the end of next lecture will almost all be in what nodes from the fringe do we pick first. How do we prioritize which node to pick? Because that will determine which part of the search tree we explore, and we know we want to explore as little as possible of our search tree and find a solution. Okay, let's look at this in action. We are going to do a tree search on this state space graph here. I'm going to have two parts here. On the left, I'm showing the search tree. On the right, I'm going to show the fringe as we go along. Okay, search tree starts with the start state, S. So S is our start state, G is our goal state. That means our fringe just has a state S on it. We call the successor function. What we get D, E, and P. What that means for our fringe is that S got off the fringe, and now we have SD, SE, SP on our fringe. Okay, now we have three nodes in our fringe. We pick one of them. Which one? D? All right. E? Okay, E sounds good to me. So we pick this one here, just this one here. Pick that one for expansion. The successors are H and R. So H and R. And on the fringe side, what happens is this goes off, and instead we get SER, SEH. Okay, now our fringe has four nodes on it. We need to pick one of them. What's your pick? Somebody picked H, but that's kind of a poor choice. Anybody wants to make a different choice? R, all right, let's go with this one here. Pull that one from the fringe. That one disappears from the fringe. Its successors go onto the fringe, so we get S, E, R, F. Only one successor. Get F over here. Again, four on the fringe. We pick one. How about we pick SERF, this one here. Pull it from the fringe. Put its successors on the fringe. SERFC and SERFG. Same thing here. C and G. We have five nodes on the fringe. Let's pick one. How about this one over here? What will happen now? After we pick that one, we enter this part of the code here where it says, if the node contains a goal state, return the corresponding solution. That's what's happening now, and we return SERFG as our solution. Okay, that was one search strategy. That was just us eyeballing what we might pick. A piece of code, of course, cannot rely on us to suggest which one to pick. So we're going to look at a few different strategies now. Yes?
When we're coding this, does it matter the order, like fringe? Should I take the node from it, add its successors, and then build a search tree, or take the node, add the search tree?
So how do you do this in code? In code, you could do this in multiple ways. One way to do it is to explicitly keep track of a fringe. It's a very simple way of implementing it. You'll have a little bit of memory overhead because you're effectively storing kind of the upper parts of the tree multiple times in some sense. But it's an easy implementation to make. That'd be one way to go. It's probably the recommended way to go. You implement this as a priority queue in some sense, that your priorities encode what you want to pick first from your fringe. You could also explicitly have a tree data structure there and keep track of where the leaf nodes are and so forth. That's much more complicated to implement. I probably wouldn't recommend it, but there is some sense alternatives in how you would implement these. You would not implement both. Okay, so let's look at the first search strategy, depth-first search. Straight down. What would happen if we run depth-first search on this same problem that we just did with our own guidance of picking nodes? Okay. I visualized the entire search tree here. Keep in mind, depth-first search will not first build that search tree and then explore it. It'll build it on the fly. But this way we can visualize what part of it that we're actually building, right? So we start with just this part in our search tree. Then the circled nodes are added. At this point, the depth is equal for all three of those. So we break ties. We break ties alphabetically. So we go with D. How about now? Well, these are the deepest ones. Again, a three-way tie. We'll break ties alphabetically. Go with B first. Now, this is the deepest one. Keep in mind, we haven't built that search tree ahead of time. So at this point, we don't know that this is a dead end. At this point, we actually go with the deepest one, which is A. We would call the successor function on A. The successor function would say, oh, no successors. At that point, we'd know that that's a dead end, and it would be out of our fringe, and it'd be gone. What's now deepest, C and E. Breaking ties alphabetically, we go with C. We again have an A, that's a dead end, but again, we do that work. We have to call the successor function on it. And we keep working, sweeping in some sense left to right, until here we pull the goal, node that reaches the goal from our fringe, and we're done. So we explored everything over here in our search tree. All right. What are the properties of this algorithm? In general, that's what we want to do. We want to somehow abstract away from this particular example and say, what in general can we get running depth-first search? Completeness was the question of whether we're guaranteed to find a solution if one exists. Is depth-first search complete? Yes, but under some assumptions, right? What if you had a case where you would go down all the way on the left and there would be a cycle, you'd keep going and going and going, you'd keep going forever. So under the assumption that you have a cycle check in there, that you wouldn't have a plan that cycles through things, it is complete. So you need a slight tweak to what we've done, but under that tweak, it would be complete. Optimality. Are we guaranteed to find the least cost path using depth-first search? No, it's just finding the leftmost path, right? Time complexity. How much time does it take? Well, it's hard to say without making any further assumptions, right? Space complexity, same thing there. Hard to say without making any further assumption. We need to define some variables of our problem so we can define those notions better. So if we look at a cartoon of a search tree, looks like this. There's a start node, and then it grows layer by layer, right? Now let's define some notation. B is the branching factor. It's an upper bound on the number of successors any state can have. M is the maximum depth. For some search trees, M would be infinity, right? But in general, there's some number M that is the maximum depth in your search tree. Okay, then this entire search tree has B to the M nodes. And the bottom layer, B to the M minus 1, the layer before and so forth, and just one node at the top. You sum this all together, you get order B to the M nodes in your search tree. It could be very large. Solutions could appear at various points in your search tree. There could be a solution down here, one up here. There could be more solutions. Often there's multiple ways of achieving the goal, and there could be even multiple goals. And so the questions we can now ask is, what is the time complexity of depth-first search if we assume a branching factor of B and a maximum depth of M? And with time complexity, what I mean is the worst case. What's the worst case for depth-first search of how long this would take? I hear B to the M. Why? Well, the worst case is when the solution is sitting right there in your search tree, right? You sweep through the entire search tree until you finally find the solution. So depth-first search would have a B to the M running time complexity. How about space complexity? What I mean with space complexity is how much do I need to store on the fringe? How many states can be on the fringe at any given time? Somebody has a suggestion there. So why B times M?
So at the very bottom, at each level, you can have -1 other branches that.
Correct. So I'm going to say this again because maybe not everybody could hear you. So the answer was B times M. So for time complexity, we had order B to the M. Space complexity, order B times M, which is quite different. The idea is that whenever you're running your search, you are somewhere in your search tree. As you are at some point in your search tree, what are you storing on the fringe? Well, let's say this is the first layer. At this point when you're here, everything that's to the right of that node that you're currently explored on your fringe is still on your fringe, right? So this here is on your fringe. Over here, all this will be on your fringe. Over here, not all that. That's too big. Over here, we'll have all this guy's options on the fringe. Then from this guy, we'll have a bunch of options for down here. Then all this will be left on the fringe, and so forth. So as you work down your way in that search tree, you see where you're currently at. Along that path, you're considering at most for every node B successors. So at every level, there might be B things on your fringe from that level, and there are M levels. So B times M. Yes?
Just clarification, would be the branching factor? Is that the average of the branches or the maximum?
In this case, we assume the maximum. And you could also assume that it's just constant for the purpose of what we're doing here. All right, so we went through this. Breadth-first search, different strategy. What do you do in breadth-first search? You can go layer by layer, a different way of mining for your gold. What would happen for our toy example? Well, we again start with just this node over here, expand. Now we have 3 nodes on the fringe. Which one to pick? All equally deep. Breadth first picks the shallowest one, but they're all equally deep, so we break ties alphabetically, D first. Now we have 5 nodes on the fringe. These 2 are the shallowest ones, so those are preferred by breadth first search. They're equally preferred, break ties alphabetically, we pick E first. Now we have just this one at the second level. No tie breaking needed. That's the best one according to breadth first search. We expanded, and now we have all these nodes on the fringe. Again, we have to break ties. We'll do it alphabetically. And what you see here is that you stripe through this search tree layer by layer by layer until at some point you reach a layer where you have a node that reaches the goal. And once you expand from there, you would find that you reach the goal and stop your search. Okay, so what are the properties for breadth first search? What nodes does it expand? Well, it expands all the ones that are, in some sense, above the closest by goal node. Right? Because it goes layer by layer until it reaches a layer where there's a goal node. So, to quantify this, we're going to introduce a new variable, S, and we say that the goal at the highest up in the tree is at level S. So S is how deep your shallowest goal is. And then the number of nodes expanded by breadth first search is order B to the S. So effectively it's reducing the depth to the depth of the shallowest goal. How about space? How much space does it take to run a breadth first search? Well, let's think about it. When this is happening, this search, let's say you were in your search somewhere over here. What's on your fringe? This entire layer is on your fringe, right? How many nodes in that layer? As you go layer by layer, worst case is the last layer that you're at, which is this one here, which has B to the S nodes. So you'll have B to the S nodes on your fringe right before you find the solution. That's really bad. So exponential in the depth of the shallowest solution. Is it complete? Yes. If there is a solution, it's going to find. It's going to keep striping through that tree until it finds the shallowest solution. All right. A little caveat here. So the one thing here is, of course, the assumption is that your solution is at a finite level. If your solution is infinitely far away, then you might not find it, but those are kind of weird mathematical problems. Is it optimal? In some sense it is. It finds the shallowest solution. But in some sense it's not. And in this class we'll say it's not optimal. And the reason we'll say it's not optimal is because it's not accounting for the cost of the actions. It's optimal if the action cost equals 1 for every action, no matter what action. In general, if the cost for every action is the same. But if your actions might have different costs depending on which action you take, it's not going to find necessarily the cheapest way of getting to the goal. So, not really optimal, only optimal if your action cost is equal for all actions. Okay, let's do a little quiz here. Depth first search versus breadth first search. When will breadth first search outperform depth first search? And when will it be the other way around? How about the first question? When will BFS outperform GFS? Who has a suggestion? Yes. When you're looking for the shallowest path, then breadth first search will find that, and depth first search, maybe, maybe not. No guarantees there. Any other times it might be better. Here.
You have much more paths between nodes than the...
We have a lot more paths between nodes than nodes itself. So you would have a very large branching factor, which would be bad for both of them.
But the DFS and more.
I see. So you're saying, okay, good point. So the point was that if you have a very large branching factor, depth first search goes really deep. So it's and it's exponential in the branching factor, of course, and it goes deeper than breadth first search. So it's going to be even worse to do depth first search with a large branching factor than breadth first search. Absolutely. Yes? Exactly. When the goal is very close to the initial state, but you don't know where it's going to be, then you know it's close, breadth first search will find it and will not have to do a lot of search, whereas depth first search might go off on this really deep thing that just leads nowhere. Trickier one. When will DFS outperform BFS? Over there.
When you have a smart tiebreaker.
We have a smart tiebreaker, exactly. What do we see with DFS? It's going down off to the left. What does going off to the left really mean? That's just a tie-breaking, right? The tie-breaking happens to put us in a particular direction. If you have a lucky or smart tiebreaker that can guide you to where the solution might be, then DFS might just channel right to the solution. Of course, we need somehow a smart tiebreaker, which we don't know yet how to do, but that would be good for DFS. Yes?
Does DFS also perform BFS if you have a very long narrow set of solutions, so relatively low branching factor and very high solution depth?
So that's another idea there. Depends on how many solutions you have. Let's say all your solutions are really deep in your tree. Let's say they're all at the bottom. So no matter what, you have to search till the bottom of your tree. And let's say there's a lot of solutions at the bottom of the tree. Maybe half of the things you reach at the bottom of the tree are solutions. Then DFS will shoot right down to the bottom of the tree and right away find a solution. Whereas BFS will be slowly making its way down and then finally get there and find a solution. Another case where DFS could outperform BFS if you run into memory limitations. We saw that for breadth first, the amount of memory you need is exponential in the depth that you're at. Whereas for depth first search, that's not the case. So memory limitations could make DFS your algorithm of choice. Okay, let's look at a little comparison here. What we have here is a demo. I'm not telling you ahead of time whether it's going to be DFS or BFS. You get to shout out which one it is. Breadth first, depth first. Okay? Green is the starting state. Red is the goal state. Actions are to move northeast, southwest. And what you will see visualized, you'll see a dot on the screen for every state that has made it into the search tree. So you'll see how the search tree is growing as the search algorithm is running, visualized on the state space. All right, I'm hearing BFS. Why? What are we seeing here? Well, everything that's equally far away over here it's expanding things in kind of a radial way where everything that's equally far away kind of comes after each other, and then the next distance gets explored and so forth. All right, let's look at another one. Again, could be BFS, could be DFS. I might be trying to trick you. DFS with one of the worst possible tiebreakers, right? It's going left, 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 and that's not at all getting it to the goal. Bad case for DFS. Now, it turns out you can get the best of both worlds with something called iterative deepening. So what happens in iterative deepening? You run a depth-first search with a depth limit of 1. If you find a solution with a depth limit of 1, then you're done. You found your solution. If you didn't, then you run depth-first search again with a depth limit of 2. If you found a solution, you found the shortest path in terms of number of actions, right? This happens to be at depth 2. If you didn't find a solution, well, then you continue. You run a depth-first search with a depth limit of 3. Keep doing this until at some point you're running a depth-first search with a deep enough depth limit that you do find the shallowest solution. So what's nice about this? You find the shallowest solution just like breadth-first search would do. What's also nice about this is that you don't have the memory complexity of breadth-first search. Because you're running a depth-first search, your memory complexity is still order. This has a memory complexity of B times S for memory, or order B times S for memory, and order B to the S for running time. So it has the same complexity as breadth-first search in terms of running time, same complexity as depth-first for memory, and it finds the solution with the least number of actions. You might say, well, going down this thing here, I repeat some work. When I search with a depth of 2, I'm redoing the work for a depth of 1. When I search for a depth of 3, I'm redoing all the work I did before. Yes, you are. And the benefit you get from that is that you're not keeping everything in memory. You have less memory needs. You are redoing some work. How bad is the work that you're redoing? It's actually not that bad. Keep in mind, when you look at this tree, this picture is not the real picture. Keep in mind, depth 1, 1 node, depth 0 or 1, whatever you want to call it, 1 node. Then here you have B nodes. Here you have B squared, B to the third, B to the fourth, and so forth. So the size of the tree for a given depth grows exponentially. And so really when you search up to a given depth, anyway, all the work you do to get to that, explore that last layer is so much more than the work you did when you went one depth less in the previous round. So when you do this, is it wastefully redundant? No, because this last search with depth of S here depth S, that last search is the one that essentially dominates everything else anyway in terms of running time. All right. What we haven't looked at yet, we now can get the best of both worlds between depth first and breadth first. We haven't looked yet at costs. So here we have our toy problem again, but now there are costs associated with actions. So every edge has a number on it. That number is how much it costs to traverse that edge. Okay? First algorithm we'll look at is called uniform cost search. It's a bit of a tricky name. The costs annotated on this graph are not uniform. They're far from uniform. Right? Uniform cost search, uniform refers to the algorithm, not to the problem you're solving. The costs are not in any way uniform. Uniform means the same. They're not the same. The algorithm is uniform cost search. How does that proceed? Well, we again start with the start state. We expand that one because there's no other option. Now our fringe has 3 nodes in it. S to D, S to E, S to P. S to E is the most expensive one. S to P is the cheapest one. That's the one we'll pick. So this is the cheapest one so far. Cost of 1 to get to P. We pick that one from the fringe, expanded, and now we have a fringe with 3 nodes. Cheapest one is over here. We expand that one, and we keep expanding the cheapest one on our fringe as we go along. Now this one here. Now it's going to be this one here. We'll keep working through the search tree, but again, we're building this up as we go. The search tree doesn't exist. We're building it up partially as we go along. What happened here? This is really important for the definition of the algorithm. At this point, actually, we have a node on the fringe that achieves the goal. That doesn't mean we're picking that node next. The algorithm always picks the cheapest one. The cheapest one right now is this one over here, E. That one's picked next. Now the one reaching the goal is the cheapest. It gets picked, and your algorithm will say, oh, this one reaches the goal. Return that one. This will turn out to be critical. Next lecture, we'll have a proof of optimality. And this is required for your algorithm to be optimal, is that you don't just grab the goal when you put it on the fringe. You have to wait till it's its turn to come off the fringe before you can declare success. So it looks a lot like breadth first search, but the layers now are not just horizontal through the tree, but they're according to the cost that you incurred to reach certain parts of the tree. What are the properties of uniform cost search? Well, what nodes does it expand? That's a C. Well, we're going to define something new here, C star. C star is the cost for the optimal plan that reaches the goal. So the cheapest way of reaching the goal has a cost of C star, new symbol we're introducing. Now, if let's say that sitting somewhere here, we achieve that one with a cost of C star, what nodes have we looked at before we declare success with this node over here? Right, any node cheaper than C star. So any node with cost to reach it smaller than or even equal to C star. How many can there be? We'll introduce an extra new symbol, epsilon. We say that every action has a cost of at least epsilon. This will help us. Right? This means that you cannot go through an infinite sequence of actions that have cost 0, because that would be weird stuff that would cause some issues in what we're doing here. So the minimum cost is epsilon for any action. That means that any plan that has a cost less than or equal to C star has to be at depth at most C star over epsilon. You could never go deeper than that, because if you went deeper than that, it would be a plan with a cost more than C star. So how many nodes can we expand? Well, this is now our effective depth. And the number of nodes we'd expand would be branching factor to the power effective depth, which is C star over epsilon. That's the number of nodes we expand in uniform cost search, worst case scenario. Okay. This is text saying the same thing. So exponential in the effective depth, we can't really hope for anything better, right? As long as we, with the things we've seen so far, if we stop sooner, we have not excluded certain paths that are cheaper. And so as long as we don't have excluded that they might lead to the goal more cheaply, we cannot guarantee that we reach the goal optimally. How much space does the fringe take as we do this search? Well, this is a lot like breadth first search, right? We're effectively keeping everything on the fringe that has the lowest cost, that has a low cost so far. So worst case, just like depth first search, is B to the effective depth in terms of memory complexity. Same reasoning there, that could be sitting on the fringe right before we declare success. Again, C star over epsilon is the effective depth of our search. All right, is it complete? Well, it is as long as there's a lower bound on the cost for each action. So as long as there's some epsilon different from 0 that lower bounds your cost of actions, it's complete. Is it optimal? Under these assumptions, yes, it's optimal. It will find the optimal path. We'll see it proved next lecture. Something for you to think about. We saw that we could get the best of both worlds between depth first search and breadth first search. Well, something for you to think about at home is, can you do something similar here, have some kind of iterative deepening version of uniform cost search? Leave that for you to think about. What are the issues with uniform cost search? It's nice that it's complete and optimal, but it might not explore in the direction that we want to explore. Let's look at something again here. So let's look at this example here. Let's run uniform cost search with equal cost for actions. That's actually the same as breadth first search. Uniform cost search, equal cost for all actions. Same thing as breadth first search. We saw that in action, right? If we run that, this is what happens. And even though it's great that we find the cheapest path to the goal, we also see we waste a lot of time over here. Earlier we heard a suggestion about having great tiebreakers and somehow have an idea of where the good parts of your tree are, even while you haven't been there yet. Those will be called heuristics, and those will be things we'll be looking at next lecture on how to improve where we're headed with our uniform cost search, and we'll call it A-star search then.